Hey there, wanted to let you know this is an audio only podcast, and if you get your podcast on Spotify, you can go follow me there. All right, cheers. Hello there, ladies and gentlemen. Welcome back to the Ephemeris podcast. I'm your host, Aphelion. I'm going to save my commentary on my hiatus recently for the end of the episode um, because I do want to keep our new viewers around here a little bit. If you do not know what this podcast is about and who I am, once again, I'm Aphelion, and the Ephemeris podcast here is a podcast where we investigate new things that are happening in the world of astronomy, and we do that by looking into new news articles that come out. Um, like in the ballpark of about like 1 or 2 months ago, I'd say. That's usually where I'm pulling my articles from. So, yeah, without further ado, I should talk about what we are discussing today, and that is neutron stars. That's the topic for the articles that we're going to be looking at today. The first one is going to be about a vampire neutron star, as they call it, that is blasting out relativistic jets, and we have a lot to uncover about that whole story. And the second story is one of the universe's most extreme dead stars that has recently come back to life. So, let's get into that first story we just talked about. Relativistic jets being traced back to violent neutron stars. And not only that, it's not just a violent neutron star, it's also a companion star that's um, in the mix of this whole system we have here. So, if you're not familiar with relativistic jets, they're just a description of jets of matter that are traveling at um, near light speed, pretty much. And neutron stars, if you do not know what those are stellar remnants that form after a star many times larger than our sun explodes in a supernova event and contracts into a ball of neutron degenerate matter. We covered a specific type of neutron star in season 1 of this podcast. If you want to check that out, it's about pulsars. But yeah, that's what neutron stars are. And themselves, the neutron stars themselves, they are extremely powerful. But where the story gets interesting is when we put a regular star alongside it. And when that happens, the neutron star begins to feed off of what we call a companion star and its material. And in a way, the neutron star comes back to life because when these neutron stars exist, they're in their stellar remnant phase, which means they don't have much to keep themselves busy with. They've burned through all their star burning or star forming material, and they're just left with a pretty useless matter that tends to be highly magnetized. But when you give them gas and dust from another star, their environment initiates thermonuclear processes on their surfaces and it erupts the new material out of their poles at really fast speeds. And that is what we think the relativistic jets are. If you want to create an analogy that helps you visualize this a little bit, it's like you can think of a neutron star as a rapidly spinning saw that's waiting to come in contact with a piece of wood, which the wood would be kind of like a companion star. So let's talk about the details of these relativistic jets because it's real easy to say that they're thermonuclear processes that create these near speed of light traveling material. But what are the details? That's the purpose of the article we have here. The quote that it gives us to sum it all up is scientists have revealed one way to measure the speed of those jets and connect the values to the qualities of both a neutron star and the unfortunate binary companion star it feasts on. This could ultimately help resolve this jet-related dilemma and perhaps offer information about other objects that strip matter from a companion star top, such as supermassive black holes. So before the study, scientists had several detailed theories for the mechanism generating the jets. The original theory was that the rotation of the material stripped from a victim star as it spirals in just got launched, pretty much. They gathered a lot of energy, and out the system they went. But another theory is that the rotation of the star itself created the jets. So just thinking about perhaps the accumulation of matter at the poles and sort of their motion a little bit, and it got launched because of how highly magnetized the neutron stars are at their poles. But now that we've added thermonuclear processes to the story, we're taking one step closer to the answer of the origin of relativistic jets. That's what we're really hinting at with all of the quotes that are being integrated here into this story. So, yeah, that is pretty much the news that we have for this vampire neutron star that we have discovered in many others, and the details about them. But there's another story that we have about neutron stars that's going to take us a little bit deeper into the objects themselves. And it's about a neutron star that has come back to life, and in a very unusual way. Its name is quite long and tedious with a lot of numbers in it. I'm not going to say it because it's just a waste of breath. But it was discovered in 2003, and it's a magnetar. It's a younger version of a neutron star that generates a huge and very strong magnetic field, even stronger than your typical neutron star that we've already discussed. But this specific neutron star, it kind of disappeared from us in 2008, and it's because we just stopped receiving light from it. Like, we would typically receive radio waves from the object, but that ceased to happen in 2008. But in 2018, it came back into view, and with a completely new look. Not in the way that we would change our looks as humans, but a lot of things changed about it. The frequency of its light was way low, and the star was wobbling. And if it's not already evident, the wobbles aren't slight oscillations. They're much more major than that. It's a systematic change of the magnetar that we did not expect. So how did we find out about this wobble? Well, it was an odd phenomena detected in the light we received called polarization. And yes, it is the kind of polarization you might have in your sunglasses. Just to be very clear on the definition of polarization here, it's the orientation of light oscillating in multiple directions into just one direction. If you were to take like a introductory optics class, perhaps, if you wanted to visualize what polarization or a polarizing material might do to light, it's kind of like trying to send a string through a grill. Where you put a rope through it, and you can only shake it one way. So like, if you imagine that one string of light is trying to pass through this grill that is a polarizer, it'll only pass through in one direction, and that's essentially what polarization is. Hopefully the verbal description makes sense. It is sort of more digestible if you see it in visual form, but I tried to put it into verbal form there for you. So that's what polarization is. The reason why this occurs with light exiting a magnetar, there's a lot of theories. The main theory is that the magnetic field, presumably because it's extending from pole to pole, it's so strong that the matter in the field filters out all light except ones that are oscillating in the direction of the poles. That's kind of the idea I got with this object that I was researching here, but it could also happen because of the nature of the particles near the magnetar are a little bit different, but the observations do not match this theory, sorry. Light at its core is an electromagnetic wave, which is also an important thing to mention, and obviously it has certain particle-like behaviors. That's why we mentioned the wave-particle duality of light. So the sort of field extending from pole to pole, creating this single oscillation, it's plausible. Maybe not so much the particles that are near the magnetar. What's extra interesting about the polarization of light in this case is that it changes the orientation of the object when we receive its light. I can't explain that to you because this is still a puzzle that kind of came with the data that astronomers are still trying to figure out. They observed a precession of the magnetar. That's what we're describing here. It's not like, a 90-degree rotation like you would do to an image when you're editing it, but it's a precession. It's slight tilt, a couple degrees perhaps. And the polarization effect we know was creating this observation. And again, theories exist of some material existing beyond the star that alters the light in such a manner, but it's still very speculative. What I will say, though, is we can kind of tie in the first article and say that perhaps the information we get from future research of revived neutron stars could help us understand the nature of material surrounding a neutron star and maybe help us figure out what part of the plasma that might exist around a magnetar, how it can create polarization and visual precession. So yeah, that's kind of how I wanted to take these two articles here, bring in a little bit of an introduction of this vampire neutron star and sort of neutron star binaries, I guess you could call them, and what's going on with the relativistic jets, and tied in a little bit with this neutron star that has come back to life and some of the unusual environments that we see with it. And yeah, that's what I've got to say about neutron stars. Very quick episode. I did want to get this out very quickly because obviously it's been a long time since I published an episode. It's been around 3 weeks at this point, and life just got very busy with the academic year coming to a close and stuff. So I didn't have much time. I was very focused on other things, but I did manage to get some shorts out midweek. Hopefully you all enjoyed those. I did want to put out some content to make up for the fact that I wasn't putting out full-length episodes, but hopefully with this episode out, I will be able to do things more so in advance and prevent these hiatuses. So yeah, that's all I've got for this episode, by the way. Hopefully you all enjoyed. If you did enjoy, you made it through to the end of the episode, I really appreciate you supporting this content that I'm creating here. If you listen to audio only podcasts on Spotify, go ahead and follow me on Spotify. Perhaps that's a more convenient way for you all to listen to this episode. If you like sticking around on YouTube though for this content, I would sincerely appreciate a subscribe on YouTube, and make sure you click that bell icon as well, because YouTube is not very good at recommending my content. So yeah, that is all I have to say. I wanted to make this one a quickie, and yeah, I will see you all later next week. Peace.